In this video, we'll continue exploring the metacircular interpreter by discussing the MCI's representation of the environment. So recall, an environment is the data structure of scopes and variable bindings that provides the context for evaluation of some expressions. In the MCI, the environment is just a list of frames, though. So in the code, not far after all the implementation of the abstraction barrier we discussed in the previous video, so around line 237, we see some development of an abstraction barrier representing this environment. And we can see the first two functions here, enclosing environment and first frame, correspond to accessors for frames out of the environment. So if an environment is just a list of frames, so env here is a list of frames. If we want to get that local frame, that would be the first frame in that list. So first frame here corresponds to the local scope of bindings. And the enclosing scope, where all, let's say, the free variables will be stored, is in the enclosing environment. Now we can see in the implementation of these things, the first frame is literally just the car of that list, and the enclosing environment is the CDR. So it's just aliasing for accessing two parts of a list. So the environment itself is just a list, where the elements in that list are each frames corresponding to individual scopes, where the closer you are to the front of that list, the more localized you are in terms of nesting of these scopes. So if we have accessors for the different parts, we also have essentially a predicate here for determining whether something is an empty environment. It's actually just an alias for the empty list. So an empty environment is just a list with no frames in it. And now we can see frames are constructed in this function here. This function is given a list of variables and a list of values and creates what we would call as a frame. But we can see that that is actually just implemented as a pair. So it takes the list of variables, list of values, and says, okay, I'm going to keep these two things together. So it's a pair where the car of that pair is a list and the CDR of that pair is a list as well. Something that looks like this. So if we have some sort of frame, we have a list of all the variables and a list of all of the values. Okay, so accessors for individual parts of a frame. So we have the frame variables and the frame values, again, are just aliases for car and CDR, where if we want the variables, that's the first part. If we want the values, it's the second part. Again, going to our picture, if we take the car of this list, it gives us the list of variables. If we take the CDR, it gives us the list of, the car of this pair gives us a list of variables. The CDR of this pair gives us the list of values. Okay. So we have constructors, we have accessors. What else do we have? Functions for extending. Okay. So a mutator for adding a new binding here. Line, I have it 260. That's not the right one. Anyways, adding a new binding to a frame. So if, going back to our picture here, if this is our list, our frame of bindings for a given scope, if we want to create a new binding, so if let's say somebody put a define at the top of that scope, what we need to do is add a new variable into this list and a new value into this list at the corresponding location. So the way this works is we're going to just mutate the existing lists there. We're not going to construct new ones. So this takes the existing values, so that's the list of variables, and conses our new variable onto it. So if this was a list, we're going to cons a new variable to the front of that list, and if this is a list of values, we're going to cons a new value onto the front of that list. So we'd have, let's say, z is 0 on the front of either of these lists. Okay, and that's all this is doing, and it's going to mutate the two bindings to point to these new two lists instead of the old ones. All right. Now, if a frame is just this pair of lists and an environment is a list of frames, essentially what we have is this frame inside a structure that looks like this. So we have at the top here is our environment, so there's our top level variable env, similar sort of thing that was passed into the eval function, for example. And that has essentially the structure of a list, right? The car points to a value and the CDR points to the next item, all the way down until we end up with the null terminator. Okay. So the frontmost element in this environment is going to be the localmost frame of evaluation. So frames look as we've seen them. And now if we want to know what's in the enclosing scope, we go to the CDR of our environment, and then we take the next frame. So this would be in the enclosing scope in the global scope, for example. And if our variable that we're looking for is not there, then we'll go into the next frame, for example, into the primitive, and we'll find plus, times, and all the other built-in operations there. So this is the general idea of the environment in the MCI. We have a bunch of different frames all strung together as lists. All right. So the real question is, what happens when we want to do things to this environment? We want to add new variables or new scopes. So for example, when we do a function application, we need to extend the current environment to include this new activation record for the newly applied function. That needs to have bindings for all the parameters to their arguments in a separate local scope. So how would we extend this environment to do that? Well, because the environment is just a list, and the localmost frame is at the front of that list, it is very simple to actually extend this environment. All we have to do then is just essentially cons a new frame to the front of this list. So if we had some nested function inside local, it could look like this, where environment points to that nested function now, which has all of its bindings. I didn't bother coming up with examples here. But then the CDR, so the enclosing scope around that nested function, would be the local function, and then the global and the primitive. So we just cons to the front of that a new frame, and now we have an extended environment. So let's see what that looks like in the code here. So this extend environment function, you might recall, I'm just going to scroll to the top real quick here. Where is it? Extend environment. So this is used inside the apply function when we go to determine the value of compound procedures. Right? So if we want to say apply f to the arguments 1, 2, and 3, well, we need to create a new contour where the parameters, let's call them x, y, and z, are bound to the values 1, 2, and 3. And that's what this is doing. It's calling extend environment. It's going to provide the list of the parameter symbols, so x, y, and z, the list of argument values, so 1, 2, and 3, and the existing environment, so everything, let's say, from local and to the right of that. Okay, and what we're going to do is extend that by creating a new frame and attaching it to the list. So let's see how extend environment works. Jump to the definition. Okay. So extend environment is given a list of variables, the symbols, a list of values, the actual values, and the base environment in which we're extending. So the first things first, we have to make sure that everything's structured appropriately. We have the same number of variables as values, and if so, that's great. We can essentially extend the environment with a single operation. We say make a brand new frame, and then two operations, I guess. Make a brand new frame, and then cons that new frame onto the base environment. So make frame we saw just says cons variables and values together, so create a pair of those two lists, and then cons that to the front of the rest of the environment. And then the rest of this, the bulk of the function actually, is actually just determining which which list was too small, so we can report the appropriate error if there was one. Okay. So extend environment is how we create this new local scope, for example, in apply before the procedure's body is evaluated in that new environment. All right, and now on to representing variables in these environments. So first things first is determining the value of variable, right? If I just said eval the symbol x, well, if I run this right now, I'm going to get an error because there's nothing in the global scope called x. But if I were to define something, then it would find that symbol x. So if I had said something like define x to be 3, and then asked what's the value of x, it can tell me, sure enough, the value is 3. Now, how does it do that? Let's start with eval. Up at the top here, eval says, is it a variable? If so, then we're going to look up variable value. Given expression is just some variable symbol, and environment is the context of evaluation. So let's first see what this predicate does. So variable just says, is this thing a symbol? So anything that looks like x or y or hello, anything essentially that starts with a quote when we type it, like this, that's just the symbol hello. Okay. So if it's a symbol, we're going to assume it's a variable, and then we're going to look up that symbol in our environment. And where is that now? All the way back down. There it is. So just after the extending environment, so we have lookup variable value, and we have the variable symbol that we want to look up, and the environment in which we want to find it. And now this works in essentially in a nested loop sort of structure. And the reason being is we have two directions to search through. I'm just going to go back to the diagram here. So if I want to find some symbol, and actually just go back to a simpler diagram. If I want to, for example, find the symbol C, if my environment is this entire thing, so if I was given this pointer as my environment, then what I want to do is first look through the local environment and say, is there a C in here? Now, because these are lists, I have to process through these lists using the same recursive techniques we've already learned for processing through lists. So check one at a time. Is A equal to C? Is B equal to C? No. Is C equal to C? Sure enough, there's the value. So I want to return the associated value. Now, if I was, for example, looking up the symbol x, if this was again my starting point, I'd first have to make sure that x wasn't found locally, right? Because if I had a local x, it would hide any enclosing free variables. In this case, we don't find that. So we go through this whole search. We come up empty-handed. So that says, come back to the top here, move to the next frame, and repeat that search. Okay. If we don't find it there, then we go back to the top and we repeat the search here. If we don't find it there, eventually we'll run out of frames because this is just a properly terminating list. So if we ever reach this endpoint, that means the variable's not found, right? If I was looking for, let's say, a Z, I don't find it here, I don't find it here, I don't find it here. I've run out of frames, the variable doesn't exist. Okay. So how does lookup variable value actually do that? So we have this env loop function, which corresponds to the bulk of this whole program. And inside that env loop, we also have this scan. So scan is what's used to look through one single frame. So let's start there. Let's just see where it starts here. Scan. Okay, so frame here is the first frame, which we saw was just the car, so that'll be the localmost frame. And then what scan gets is a list of variables and a list of values. So essentially we access those two lists and we pass them into scan as vars and vals. And now scan's just going to recursively look through this list of vars to see if the item we're looking for is there. So if we're out of items, then we're done. So we'll come back to that in just a second. If the item that we're currently looking at, so the car of our list, is equal to the symbol that we're looking for, this var that was passed in, then we return the head of the values list. So back to our drawing here. If we're going through this and if we're, let's say, looking for A is at the head of our list, so because that does match the symbol we're looking for, we'll return the head of this list. If that's not the case, then we're going to CDR down. So we're essentially going to hide this A and this 1, and our list will be just this section here from B and C onward. Okay? And at that point, if the symbol we're looking for was B, it would be at the head of the list, and 2 would be at the head of the values list. So again, if we find the symbol at the head of the variables list, then the value should be at the head of the values list. Okay, so that's the success case there. If the value we're looking for is at the car of the vars, then return the car of the vals. Otherwise, then we just CDR down. So we shrink both of these lists, so they're shrinking in tandem or equally, and then we call scan again. Now eventually it's going to search through all these things, and if it can't find the item, we'll run out of items in our lists, right? Vars will become a null list. At that point, we're going to call env loop with the next environment in the list. So enclosing environment, recall, is just the CDR of this env. Going back to our picture, if this whole thing is our env, the car points to here, the CDR points to this. So now this is our list. And now the first frame out of this list is the enclosing scope of the original list. It's the global scope now. And we repeat the same process, looking for all the different values, or through all the different variables to see if any of them match, and if they do, returning their associated values. So calls enclosing environment on the, calls environment loop with the enclosing environment. So CDRing down again and again and again. All right, and that's the entire process. If eventually it doesn't find that, when we call enclosing environment, it actually when we call env loop, keep doing that, it jumps back up to the top of this function, defines scan but doesn't run it right away, and walks through these steps here. So the first thing it does is determine, are we done searching? So if we've reached the end of the list, recall this empty environment is actually just a placeholder for the empty list. So if the environment is empty, then we didn't find the variable anywhere. We looked through all the frames from the beginning to where we got to at the end, and there wasn't a binding for that variable anywhere. So we can just return unbound variable as an error. And that would be if I typed in, say, y, for example. Unbound variable y, and then I have it so it crashes the whole program. Okay, let's go back to our code, which was jumped. It was 2 something. There it is, 263. Okay. So if it's not there, it crashes, and if it's an empty list, then it crashes with an unbound variable. If it's not an empty list, then it takes the next frame from the list of environment, from the environment list of frames, and scans through that again and again and again. So that's the process of looking up a variable value. Now, there's two other functions that are quite similar to this. There's set variable value and define variable. These both work very similar. If you look at the structure of the code, we have an env loop in both of them. We have this nested scan function in them. The reason being is if we want to set a variable value, for example, we first have to find if that variable exists. If it doesn't exist, then we can't mutate the binding, right? It doesn't create a new binding, it only changes existing ones. So this entire function, set variable value, which is used if somebody uses the set operation, looks exactly the same as look up a variable value. The only difference is what happens if we find it. If we find the variable for lookup, then we just return the associated value. If we find the variable for set, then we have to mutate that binding. So in this case, we use the built-in set to say change the head of this values list into this new value. So going back to our drawing here, let's say we wanted to say set A to be 10. We go looking through this list until we eventually find A as the first item in the list. That's at the car of this list. So what we do is we mutate the car of this list to equal the new value, so 10 or whatever we wanted to change it to. Okay, so in both cases, we have to look through first the local frame. If that doesn't work, then we search through the enclosing frame. And eventually, if we run out of enclosing frames, then we say we can't mutate that variable, or we couldn't find that variable. Okay, with define it works similarly, but it is a little bit simpler. It doesn't have this env loop because with define, if you can't find a variable, if it doesn't already exist, then you create it. So in this case, it says take the first frame, the local frame from our environment, and scan through it. Okay, if we find the item we're looking for, then we'll do the mutation, very similar to what we just did with set. We'll change if the binding already exists, then we'll change the existing value associated with it. If it doesn't already exist, so if we get to the end of this search, then what we'll do is we'll call this function add binding to frame. And I think we already saw this, but let's jump to the definition. So add binding to frame, we'll pass in the variable and the value as well as the frame. So let's just jump to that. Add binding to frame takes in a variable, a value, and a frame and says set the car of this frame to this new list and set the CDR of this frame to this new list. So remember, a frame looks like this. So if we set the car that says change this to point to a new list where it has a new existing binding, so Z, and change, if we're setting the CDR, we're changing this pointer to point to a new list that has a different car as well, in this case, the new value. All right, so that's how the environment works in the MCI. Essentially, it's just lists of lists of lists of lists. And if you can understand this picture here, then you can pretty much understand the environment in the MCI as well as the environment in Scheme as a whole on its own. Now, Scheme's actual implementation is very likely to differ from this. This is somewhat of an inefficient implementation, but it hopefully is an approachable one. All right, so let's round out this discussion of the MCI by covering all the stuff at the bottom here. So there's a bunch of other stuff that happens. First off, we have to construct that initial environment. So go back to our diagram here. We have to construct this primitive environment because we're not relying on Scheme's primitive environment natively at least. So if you go looking for variable bindings, for example, they have to be in the MCI's implementation of the environment. It won't find the plus symbol unless we've defined that in the primitive. So, sorry, I'm just going to jump down to the start of the whole thing here. So the very start of the program says define the global environment to be whatever comes out of setup environment. And when we run the function, when we run eval for the first time, we pass in that global environment. So that's the pre-built, you can call it the primitive or the global environment that we're providing to the user. Okay, so setup environment does this. So it says take essentially an empty list and extend that empty list with a bunch of primitive procedure names and primitive procedure objects. So extend environment, remember, takes an existing environment, which in this case is just the empty list, and attaches or conses a new frame onto the front of it. So the new frame is going to be built up of all the primitive procedure names and primitive procedure objects, whatever those are. We're also going to define the word true to mean #T and the word F to mean #F, the word false to mean #F, just to represent true and false as words in our language. Okay, and then this whole thing returns that initial environment that we've just constructed as the global environment. So really, the only thing that we left undescribed here is what are the primitive procedure names and the primitive procedure objects. So, primitive procedure names. This is a bit of a weird way to structure it, but it is digestible once you get through it. It says map car through all of the primitive procedures. So the primitive procedures is defined as this list here, where we've constructed a bunch of effectively pairs between some symbol and this value here. But note, list is not a special form. So when the underlying scheme is running through, when I click run here, and it has to determine the meaning of all of these functions, it's going to evaluate this expression here. So it's going to get, if I typed in car, something like this, procedure mcar, the underlying scheme implementation of mcar. So what this line says is we're going to associate the symbol car with that object in our version of the environment. Similarly with CDR and cons and all of those. Okay. If we wanted to, we didn't have to use car and CDR. We could have called this first and rest. Now in our language, we can't use car CDR. We have to use first and rest. Okay. Similarly, plus the cross symbol will be associated with addition. The asterisk will be associated with multiplication. The dash with subtraction. Divide with division, and equals. Okay. And if you want, you can add all sorts of more using this very simple format. So what primitive procedure names does, remember this is the thing that's actually being used to create all of the symbols for our new environment. Essentially, it maps car across that list. So if this is a list that has all these values, if we map car across that, it's going to take the car of this, and the car of that, and the car of this, and the car of that. Essentially, it's just going to grab all of these symbols. Okay? So it's going to create a list of all these symbols, which corresponds to essentially the list here. List plus times first rest, all that. Okay? And the other half of that is essentially getting all the procedure objects, a list of those, so that we can combine them into a frame and call that our global or our primitive environment. All right, so that is here. Primitive procedure objects essentially does the same sort of thing. It maps the CDR down all of this, the catter down all of this. But it has to do one extra step, and that is to construct our objects in the form primitive and then the procedure. So it attaches the extra word onto that object. So by mapping the catter down this list, we get the procedure associated with car, the hashtag mcons and all of those, hashtag null, hashtag plus, essentially this structure of object. And we're just going to associate that with the word primitive so that when we're in eval or we're in apply, we can determine that this is a primitive procedure as opposed to a compound procedure. Okay. So this returns a list of all the procedure objects. This returns a list of all the procedure names. And then we just essentially cons those together to create the environment. And that's most of the MCI. So the MCI itself doesn't actually have any scheme itself doesn't have any error handling abilities. So in order to create native errors, or to have our code crash in bad situations, there's an error procedure here that takes in a message and optional number of arguments, displays that message, displays all the arguments, and then this line here just makes it so that we crash the code. So in this case, we're trying to evaluate the symbol error as though it were a function, but it's not because it's just a symbol. So underlying scheme will crash and we'll get this weird error. It's not as descriptive as Scheme's built-in error reporting or as Dr. Racket's built-in error reporting, but it does give us the ability to crash our code programmatically. Okay, driver loop we've already talked about. Some of this is just formatting, so displaying the string to the user is getting all this stuff out there. User print object we've talked briefly about, but here's how it's implemented. So this is, if there is a procedure object, this is how it pretty prints it. If you don't want to see that pretty printing, you can get rid of, or you can uncomment this line. Essentially it switches displaying this placeholder and instead displays the actual procedure environment. In fact, let's do one of those. Let's run our code again with that. Now let's just see what happens. We ask, what is lambda times xx? So this is what's actually being stored by the MCI with each of these procedures. So it's the list of parameters, the list of expressions in the body, and then the environment. And you can see the environment is kind of ugly to look at. It's got a list of all the names, so false, true, first, rest, cons, and all those, and then a list of all the values, so false, true, primitive procedure mcar, primitive procedure mcdr, etc., etc., etc. Okay, so that's what's stored in the environment, and then if we want, we can extend that environment with additional layers of scope. All right, I think that's pretty much the entire thing. And then it says Metacircular Interpreter loaded to the screen and actually starts the driver loop. So that is the MCI in a nutshell. Now, I imagine listening to me talking to this has been a lot less informative than reading through the code and understanding it yourself would be. Hopefully it's provided a good introduction to the material, but I strongly recommend looking through this code and making sure you understand how it does what it does, how it takes this high-level notion of interpreting an entire scheme language and essentially breaks it down into just list processing operations. All right, that's it for this chapter. That's it for this video. It's also it for this chapter. It's also it for scheme as far as Comp 3007 is concerned. So this is the last lecture in which we'll be dealing with that language. From now on, we'll be switching over to Prolog in future lectures. So stay tuned for those, and I will see you in the next video.